should be live. All good. Let me just check the audio again. Okay. Are we all good on the audio? Seems like it. Okay, so implicit types. So getting a little bit of feedback, so I just want to clear that. Okay, so anyway. All right, implicit types. Let me just do 14. And then the actual section is called type conversion type aliases and type deduction. And then we'll scroll all the way down, and then we'll do that there. Cool. Okay, anyway, enough about that. Let's continue. So, implicit type conversion. So we've done a bit of this previously in terms of implicit type conversion. For example, if you have an integer and you are dividing it by a float, that integer will turn into a float. Okay. Or a double or whatever you're dividing or times the integer by. So let's get into it. So implicit type conversion. Okay, so as you can see, we introduced it previously. So now it's the process of converting data from one type to another. Implicit conversion is performed automatically by the compiler, and we can use static cast to make the output what we want. And that is called explicit type conversion. Laptop on charge. Okay. Yes, so for example, this would need 3.0f. So when implicit type happens um, is performed automatically when an expression, um, for example, this is converted to a integer. So even though this is an integer, because we have the type of double, it will be converted implicitly to a double. But then when we have this, it will be converted. It will also be the integer value will also be implicitly converted to a double. When a type of return value is different from the function declared value. For example, this will be converted to a, so the float, so this is the main thing. So even though this is a double, it gets implicitly converted to a float type when using certain new binary. Yes, this is implicitly, the integer of 3 is implicitly converted to 3.0. When using a non-Boolean value in a statement. So this would be converted to true because it's greater than 1. So Type conversion can fail. When a type conversion is invoked, the compiler can determine whether the value of the current type is the desired type. If a valid type can be found, the compiler so yeah, because it's because this is a string, i.e. an array of characters, it means that our compiler does not actually know what to do with this, um, because a standard conversion is a string literal, whereas if it was a character, um, it would be able to do it via the ASCII conversion. Okay, so floating point integral promotion. Now it's not in my line. Okay, so numeric promotion. Because C++ is designed to be portable across. A numeric promotion is a type conversion of certain narrow types, such as a char, to a wide numeric type, like an integer or a double, that can be processed efficiently. All numeric promotions are value preserving. A value preserving conversion, safe conversion, is one where every possible source of value. Okay. Yeah, that makes sense. Numeric promotion reduces redundancy. Numeric promotion solves another problem as well. Consider a case where you want to write a function to print a a return value type of int. So you've got a void function of print int. Print int. Well, this is straightforward. Yeah. Because it keeps it in the same type. Yeah, so okay. Numeric promotional categories. The numeric promotional are divided into two subcategories: integral promotion and floating point promotions. So floating point promotions. So using floating point promotions, promotion rules, a value of type float can be converted to a value type of double, like we've learned previously. This means we can write a function that takes a double and then call it with either a double or a float value. So here we got a void return type of print double with a parameter of double D, and then in the body we're doing a standard character output of D with a line break. And we don't need a return type because it's void. So then in our return type integer main, we can print double, and then we can first of all use a normal double, and then we can print double with a float, and then we can obviously return 0. Because of floating point promotion, we don't need to use and then I'll just copy that for that one. And remember, we need to use F for double. sorry, F for a float, to signify that we want a float. Yeah, okay. So, integral motions. Using integral motions, the following conversions can be made. Signed char or signed short can be converted to an integer. Unsigned char, char8, and unsigned short can be converted into an integer if it can hold the range type, or otherwise unsigned otherwise. If a char is signed by default, it follows bools can become integers with false 0 and true becoming 1, or anything above 1 and 0. 1 and up becomes true. So, print an integer x. We got a standard character output of x. We're printing in, we got a return type of integer for our main function as always. You got print int 2. Then we're creating a short integer of s3. There is no short literal suffix, so we'll use a variable for this one. We're then printing s. We're then printing a, which will be converted into an integer of, I think, 97. I think that's it. I'm not entirely sure, but I think it's roughly that, via the ASCII. And then true will be converted into 1. Okay. I feel I understand that, so I'm not going to copy that like I did with the float. Not all widening conversions are numeric promotions. Sometimes some widening type conversions, such as char, short, int, long, are not considered to be numeric promotions, which we'll cover in the next lesson. And it's mostly academic. Okay, numeric conversions. C++, let me just first of all. So we had integral promotions. Now we're on to numeric. Okay. So there are 5 basic types of so the first is converting an integral type to any other integral type. For example, short equals 3, convert int to short, long equals 3, which means we are converting int to long, char ch equals s, which means we are converting short to char, short to char, and unsigned int u equals 3, which means we are going to be converting that should be int. We are going to be converting int to unsigned int. Yeah. Second is converting floating point types to any other so it's float f equals 3.0. So we convert a float to a double. No, a double to a float. Convert a double to a float because it's all about that to the type. Just give me a sec, I'm just going to take a quick break. Okay. Yeah, could you get like 2 or 3 of apples and pears, and then maybe one orange. Okay, thanks. Okay. And we're back. Okay, nice. All right. Okay, so yeah. So the thing we want to convert to is the obviously type, and then this is the original type or the assignment. So here it's going to be a long, remember with floats or decimal points, figures, it's double, float, long float. Maybe we have, no, sorry, long double, not long float. So convert a double to a long double. Then it is all about converting a floating point type to any integral type. So for example, int I equals 3.5. We're converting therefore a double to an integer. Then we have a fourth one, which is converting an integral type to any floating point type. So we're going to convert to a double, and we're going to convert an integer to a double. So convert an int to a double. And then finally, the fifth one is converting an integral type or floating to a boolean. So we're going to do bool b equals 3.0, convert an int to a bool, and then we'll do bool b2, which is all about converting a we're converting a double to a bool. Okay. Safe and unsafe conversions. Hopefully that made sense because they're all essentially the same type. So, safe and unsafe conversions. Unlike numeric promotions, which are safe, there are many unsafe. An unsafe one, so into an equal destination type. Numeric conversions, so there are three um, but that's just telling you safe. Numeric conversions. Oh, so we're doing safe first. What about unsafe? Oh, safety categories. My bad. My bad. Categories. One, value preserving conversions are safe numeric conversions where the destination type can exactly represent all possible values in the source type. For example, yes, like we learnt here. So if we had an integer, return type of integer for our main function, we had an integer of n and we assigned it as 5, then we converted it to a long integer. Converts a int to a long int. And then if we wanted to create a short and assign it with 5, and then convert that to a double, converts a short to a double. Right? Yes. Yeah, because the short, we're converting this, whatever the equals, to this. So n static. So in here we're doing int n static cast int. So we're converting. We want the value int, but we're converting long 3. So we're converting int to long. Oh no, so that's the expression we want to change, and we want to convert it back to int. Convert int 3 to long. Oh no, I see. So convert char C to a double and then back to a char. Okay. So static cast int, and then static cast long 3. So we are converting a integer. I see now. So convert an integer to a long, then convert it back to an int. Convert int3 to a long, then convert it back. So char c equals static cast char, then the expression is static cast double c. So that is converting a char c to a double, and then back. So that's the first type, i.e. value preserving conversions are safe numeric. Then we have reinterpretive. Which are unsafe numeric, i.e. not preservative, numeric conversions. Where the converted value may be different to the source data, but no data is lost. Signed, unsigned falls into this. Okay, falls into this category. So, for example, return type integer from main. So we're unsigned int u1. So we're converting an integer and then int n2 of minus 5. And then unsigned int u2 will be minus 5. So here we're trying to convert a int to an unsigned int, but minus 5 is over the lower limit for unsigned int. Oh, something's gone wrong. We're still good? Yeah, we're still good. Is the stream still on, or is my internet gone down? No, my internet seems fine. It was just an issue with the site. Okay. Lower than 0. Lossy conversions are unsafe. So the final third one, there was 3, right? 3 categories, yeah. So this is called lossy conversions are unsafe. Numeric conversions where data may be lost during conversion. Whereas the other one was reinterpretive, where no data is lost. So double to int is a conversion that may result in data loss. Whereas int to double is fine because they're safe. So this converts a double to an int. This will not result in data loss as the value will be 3 and will be int 3 and will be preserved. Int j equals this converts a double to an int. This will result in data loss, as 3.5 will be converted to 3, to int 3. Therefore, losing 0.5. So conversion from double to float can also result in data loss. So float f equals 1.2. This converts a double to a float. Float g, and then this number here. This converts a double to a float, but there is data loss due to precision of float, and it gets converted to therefore losing the 8, 9 on the end. Okay. Converting a value that has lost data will result in okay. So we're still in 3. Then data back. So that, for example, that we would use a long float instead, right? Assume so. Back to the source type. So double D, so we're converting a double to an integer and back. No, sorry. We're converting a double to an integer. Sorry, it's not that way. We're converting a double to an integer and then back. That's the way you do it. You do that way, and then that way. no thank you on that. Yeah, that makes sense because this is the type, this is the identifier, and this is the assignment. So we're creating the type of double. We're looking through this. We're then seeing that we want to convert 3.5 to an integer and then back. So let's just have a go at that in the actual code. So include return type of integer for our main function, and we're going to do a double D, and then we're going to do static cast double, and then our expression is going to be another static cast with an int of 3.5. So this converts a double D to an int via static cast int 3.5 and then back to a double, aka static cast double, and then yeah, why not? Static cast int 3.5. Then we're going to print our D, and then we'll see what happens. So we'll run that code. And then you see we get 3 rather than 3.5. Then we'll do the same for this. So double D2. So we're converting a double to a float and back to a double. We do static cast double. So we're going to be converting a double to a static cast float, and then this value here. So this converts a double to a float and back to a double. Static cast double so then if we were to print, not static, std standard character output D2, we should find that we actually lose some of the code or some of the value, therefore showing data loss. There you go. 1, 2, 3, 4, 5, 7. So now I just want to copy and paste that into here. Okay. I'm just going to take a quick break here, and I'll be back. Let's continue. Let's continue with finishing off with numeric conversions. So the main thing to remember, the main things to remember when it comes to numeric conversions are in all cases converting a value into a type whose range doesn't support that value will lead to results that are unexpected. For example, so we got an integer here and we're converting this number here. So we're converting an integer to a char, whereas a char has that. And then here we're printing out, or then converting C, i.e. char, to an integer. Yes. And then that produces an unexpected result. Next, remember that overflow is well defined for unsigned values and produces undefined behavior for signed values. Converting from a larger integral or floating point type to a smaller type from the same familia will generally work so long as the value fits in the range of the smaller type. For example, here we have an integer of I2, converting the int of I, which is bigger than short, to a short. We're then producing that, which should be fine. We're then producing a double of 0.1234. We're then converting that double into a float, and we're producing the float. This produces this. Okay. Um, so then, um, so this produces this. Okay. And then another point we need to remember is in the case of floating point values, some rounding may occur due to, hang on, just give me a sec, I'm just going to pause here. Hello? Are we back? We're all good? Um, it's still good on the audio? Yeah. Yeah. Okay. Let's continue then. So, yeah. So, in the case of floating point values, some rounding may occur due to um, a loss of precision in the smaller type. For example, float f okay, converting, and then here, converting from an integer to a floating point number generally works as long as the value fits within the range of the floating point type. For example, we got an integer of 10, and then we're converting our integer to a float, and then we're producing that. So we got an integer of 10, then we're convert the int to a float, and then we simply print out float. Yeah, cool. So that's all good. So that produces that, which is fine. And then the final thing to remember is converting from a floating point to an integer works as long as the value fits within the range of the int, but any fractional values are lost. For example, we have an int I equals 3.5. Then we're gonna do a standard character output of I, but this will produce Therefore, it can be seen that was lost. Okay. Narrowing conversions, list isolation, and constant expression initializers. How are we getting on in terms of progression to our types? Okay, so we probably won't finish it today, even though we've covered some of it before in previous streams. So, so where are we? Narrowing conversions. I'm just going to take a quick break here and then I'll be back. Let me just first of all. Okay. Right, I'll be back in a minute. Okay. Still good on the audio? Yep, good. Should be. Okay. Right, let's continue. So, narrowing conversions list initialization and constant expression initializers. Okay. So, narrowing conversions. They're largely unsafe because they involve things such as converting a float to an integer, i.e., like in the previous example, we had 3.5, and 3.5 will be reduced to 3. So in C++, a narrowing conversion is potentially unsafe. Unsafe. And may result in data loss. The following can be defined as narrowing. So, from a floating point type to an integral type. From a floating point type to a narrower or lesser ranked floating point type. Unless the value being converted is a const expression and is in the range of the destination type. Even if the destination type doesn't have a precision to store all the significant digits as a number. So from an integral to a floating point type. So essentially, if you're converting one type of data to another type, and they're not the same, that's when errors or data loss can occur. Okay, from an integral to a floating point type, unless the value being converted is a const expression and whose value can be stored exactly in the destination type. And then finally, the final narrowing is from an integral type to another integral type that cannot represent all the values of the original type. For example, if we converted a integer, a signed integer, whether that be short, signed int, signed long, or signed long, to an unsigned version of any of those. I.e., if we had a minus and we converted it to a signed, we would lose data to the original type. So it seems that unless a constant expression is used, so if a constant expression is used, it seems we don't tend to have a narrowing and a loss of data. Unless the value being converted is a constant expression and whose value can be stored exactly in the This covers both wider and narrower integral conversions, as well as integral sign conversions, such as signed to signed or vice versa, signed to unsigned and vice versa. In most cases, implicit narrowing will result in compiler warnings with the exception of signed to unsigned. So the best practice is to avoid narrowing conversions whenever possible. Okay. Make intentional This, as we know in previous streams and lessons, this can be done via static cast, then the type you want to use, and then expression. For an example, and I just want to practice, so I'm going to do it in the actual code. So include input output stream because we want to print. Then we have a return type of integer for our main function. Then we are going to have, so he's done a void function for some func and with the parameters of int I, and it's empty. Then we will have a double of d, which will be 5.0, and then we will call sumfunc d. This is implicit narrowing, and the compiler will generate a warning. Whereas if we did sumfunc and we use static cast and we wanted to convert d to an integer, we would do it like this. And then as always return 0 for our main function. So I run that, we should get a compile error. No, we don't. What about if we got rid of that? Will we get a compile warning? No, the compile just suppresses it. But why are we not? Oh, that's why we're not getting, because we're not having a standard output, but it's converting anyway. Okay. Nice. So the best practice is if you need to perform a narrowing conversion, use Cool, that makes sense. So now we're going to be doing list brace initialization disallows narrowing conversion. Narrowing conversions are disallowed when brace initialization and attempting when using brace initialization and attempting to do so will produce a compile error. So let's give it a go. So we'll do include input output stream, and then we have a return type of integer main int I 3.5 return 0. And there we go, we get the compile error. I type double cannot be narrowed to int within the initializer list. And then implicit conversion from double to int changes 3.5 to 3. So I'm just going to copy that as well. First of all, probably be easier to use. But if you wanted to convert it, the double to an integer, you would just again use static cast. If you wanted to convert the double to an int, you would need to initialize the 3.5 as a double and then use static cast type expression for example, and then we'll just do it because it's simple. So we'll include our input output stream. We'll then have a return type of integer for our main function. We'll set double to be 3.5. We will then do what will we do? We will then do oh, hang on, just give me a sec, I'll be back in a minute. What was it? Okay. Okay, we're back. Sorry about that, I just had to check something. Okay. Right. So where were we? Yeah, so using static cast. So now we want to do int I, and we want to do static cast, and we want to convert our double to an integer, and then the expression will be double, and then we will return 0 as always with our return function, with our main function, and then we get fine, no compile errors there. Okay. Okay. Some const expression conversions aren't considered narrowing. When the source value of a narrowing conversion isn't known until runtime, and remember that constant expressions are evaluated at compile time. When the source of the value of the narrowing conversion isn't known until runtime, the result of the conversion also can't be determined until runtime. Yes, in such cases, whether the narrowing conversion preserves the value or not value or not also can't be determined to runtime. For example, we have a void function here. We're unassigned int of u. We're then printing u. So enter an integral value. We're setting this, and then we are allowing the user to enter n. And then if they did -5, we would obviously have an error here. No, we wouldn't, because we are actually, so we're creating int n, which is a signed integer, but then our print integer requires a unsigned integer, and I assume then we are converting the n to a unsigned to signed. Conversion to unsigned. No, we're converting signed to unsigned. So I just want to, just so I understand it fully, so include input output stream, and then we're going to be doing a void function of print unsigned int of u. Note that this is signed, and then we're going to be doing a standard character output of u with a line break. Then in our return type of integer main function, we will be doing a standard character output of enter an integral value. Then we will do an int n, and then we'll do a standard character input of n, and then we will call the print function of n. This will convert the signed int n to an unsigned int, aka the parameter within print. Yeah. Cool. Okay. And then obviously we're going to want to return, as always, 0. So if we enter 5, we get 5. But what happens if we enter -5? We get that. So we'll do this, we'll do this, and then we'll do this. Okay. In the above program, the compiler has no idea when print is called, the conversion performed at that time. However, you may have noticed that most narrowing conversions have an exception clause unless the value, yes, is a constant expression. And remember that constant expressions are evaluated at compile time. That's the important thing to remember when dealing with this. When the source of the narrowing conversion is constant expression, the specific value to be converted must be known by the compiler. Yes. In such cases, the compiler can perform the conversion itself and check whether the value has been preserved. If the value was not preserved, the compiler can halt compilation with an error. If the value is preserved, the conversion is considered to be narrowing and the compiler can replace anything. It's safe to do so. For example, yes, okay, so I just want to do that again. So include input output stream, return type integer for our main function. Then we're doing const expression int n1, and then that would be 5. Then we will create an unsigned integer of u1, and we will convert n1 to an unsigned int. Then we will do a const expression of int n2, but we will do -5, and then we'll do an unsigned int of u2, and then we will call that, and then we will, as always, return 0. So this will be evaluated at compile time. This is fine for the narrowing conversion. This will be again evaluated at compile time. This will create a compile time error. This will produce a compile time error due to the value being changed and being outside of the range of a unsigned int. So let's go there. As you can see there, show errors anyway. You can see here that our constant expression evaluates to -5, which cannot be valued to type unsigned int. And they're asking you here to change it to an unsigned int via static cast. Cool, that makes sense. And then cool. So next, let's apply the rule from an integral type. So in the case of n1 and u1, n1 is an int and u1 is an unsigned int. So the conversion from the integral type to another integral type cannot represent all the values. However, n1 is a constant expression and the value can be represented exactly in the destination because it's a constant expression and cannot be changed. Therefore, this is not considered narrowing. In case 2, n2 and u2 similar. Although n2 is a constant expression, its value is -5. Yeah. Strangely, I may as well copy that. I understand it, but I'm not going to type it all out because I understand it. So there. Okay, cool. Strangely, conversions from a floating point type to an integral type do not have. So these are always considered narrowing conversions, even when the value. Even more strangely, conversions from a constant expression floating point type to a narrow floating point type are not considered narrowing, even when there's a loss of precision. These constant expression clauses are incredibly useful when initializing non-integers and non-double objects, as we can use an int or a double literal or a constant expression object for initialize values. This allows us to avoid having to use literal suffixes in most cases, having to clutter our initializations with static cast. So here we have unsigned int of 5, float of f. We can avoid static cast. So we got a constant expression of int n, and we're converting a d to, we're converting our int to a double, and then we're converting an integer, a signed integer of 5 to a short. Okay. This also works with copy and direct initialization. So one caveat worth mentioning, initializing a narrower or lesser ranked floating point type with a constant expression value is allowed as long as it's within the range, even if the destination type doesn't have precision to store the value. Floating points are ranked Yes, so that's why if you were to convert a long double to a double, you would have precision loss. If you were to convert a long double to a float, you would also have that. And then if you were also to convert a double to a float, you would have precision loss as well. That's because we are initializing. Yeah. So this is because we are using a list. Okay, arithmetic conversions. Cool. So where are we in terms of progress? Okay, arithmetic. We're definitely not finishing today, but that's okay as long as we're making progress, and I believe I am. Okay, so what we're going to do now is we're going to do um, arithmetic conversions. So this is all about operators. So consider the following expression: int 2 plus 3. What happens when the operands of a binary operator of a different type? So 2 plus 3.5. And we don't even have a type. In this case, operator is given certain operators. So operators require operands of the same type. The following operators require their operands to have the same type: binary arithmetic, these; binary relational operators, these; binary bitwise arithmetic operator, these; conditional operator, these two. Remember, conditional is all about what WTF, what are you looking for? If it's true, do this, and then if it's not true, then we do the other thing. Okay. Yeah, that makes fine. That's fine. The usual arithmetic conversion rules. So, the usual arithmetic conversion rules are somewhat complex. The compiler has a ranked list of types that looks something like this. So long double is first. long double, then we have a double, then we have a float, then we have a long, then we have a long, and then we have int. So the following rules are applied to matching types. If one operand is an integral type and the other is a floating point, the integral type is converted to a floating point. No integral motion. Otherwise, step 2. And this is all about when they talk about matching types, it's all about trying to find if we're adding, subtracting, making equal to, yada yada yada, what the actual result will end up being. After promotion, if one operand and one is that, specific special rules apply. Otherwise, the operand with the lower rank is converted to the one with the high. So if one operand is signed and the other is unsigned, so if the rank of the unsigned operator is greater than or equal to the rank of the signed operator, the sign is converted to unsigned. If the type of signed operand can represent all values of unsigned operator, the type of unsigned operator is converted to signed. Otherwise, both are converted to the corresponding. Otherwise, both operands are converted to the corresponding unsigned type. So unsigned here. So unsigned tends to take priority unless the signed operator can represent all the values of the unsigned. And then otherwise, any integral operands with lower rank is with lower rank rank. Okay. So, some examples. In the following examples, we use type ID operator. I've never used type ID. Okay, so because I've never used type ID, I'm gonna do it here. So include input output stream, include type info for type ID. So we're going to be doing return type of integer for our main function. We're going to do int I and initialize it with 2. Then we're going to be doing standard character output type ID of I, and then the name, and then we're going to do a new line. Then we're going to do double D of 3.5, and we're going to be producing standard character output of type ID D dot name. And then we're going to be doing so a type ID I plus D, and then we're going to get in that name as well. I plus D, and then a line break. And as always, returning 0. Let's see what happens here then, shall we? So you got I, i.e. the name, then you got D, i.e. the name of that, and then the type of, so this prints the identifier of, this prints the identifier of int I, and then that does the same thing but for double. And then this prints what the sum will, this prints the type that will this prints the type that will be converted to when they add together and then the said sum. Okay. And that makes sense because we see here that a double has a higher rank than an integer. So, and as we learnt here, the lowest rank goes up to the highest rank. Yeah, perfect. Although it's different. Okay, that's fine. Um, Now let's add two short values. So how long do we have on this? Okay, we'll finish this and then I think we will call it a day on there because I think that's enough for today. I think we've made good progress here. Okay, so let's do shorts. Include input output stream. Then we're going to do include type info. Then we're going to do a main function with a return type of integer. We're going to do short A, short B, and we're going to return a standard character output of type ID A plus B with a name, and then we're going to be doing space, and then we're going to be doing and then return 0 as always. Let's see what that happens. So this is converted to an integer. Interesting. This is because neither operand, aka the short, appear on the priority list, meaning we take the lowest rank, which is an int. If we were to try this with shorts, we would get an int result back. And then I'm gonna copy and paste that. Okay. Okay, final one. Signed and unsigned issues. The prioritization hierarchy making me crazy. The prioritization hierarchy and conversion rules can cause some problematic issues when mixing signed and unsigned values. So we've got, again, we'll just try it ourselves. And then we'll do a standard character output of type ID. We'll do 5u minus 10 name, and then we're going to do that should be 10, not minus, 1 minus, and then we're going to be doing 5u minus 10. Okay. Then we're going to run it. Okay, so we get J. Interesting. Because we're using a suffix. If we had done S, it would be a short. J. This produces in my compiler due to the conversion rules. Here is another type. Here is another example showing counterintuitive results. So we'll do the same, include our input output stream. We want to include type of for our type ID. And then we're going to do return type of integer from main function. And then we're going to be doing standard character output. And then we're going to be doing type ID. And we're going to, oh no, we're not. We're going to be doing standard Boolean alpha. And then we're going to be doing, so we're going to be creating a Boolean. -3 is less than 5u. So you've got a minus number, and then you've got a unsigned integer. So that means, so is -3 so is -3 less than unsigned integer? No, because 5, no, we will be converting an unsigned integer. The integer will be converted to unsigned, which means it will go to 400 million or whatever, which means this will be false. Yeah. the -3 will be converted to an unsigned int, therefore creating the overflow, and therefore the massive number of 4 whatever will be bigger than 5 u, meaning this will print false. That makes sense. Yeah, cool. Okay, so then the final one is common, no thank you, common type and standard common type T. Okay, we'll be covering that in future lessons. Okay, I think we'll leave that for today. And we've left off at cool. Let me just see how long we have left. Okay, so we might be able to finish that tomorrow, and then we get onto functions, and then we get onto references. This is really thing interesting, and then we get onto structs and classes and enums. Yeah. Okay, so close that. Okay, cool. We'll clear my terminal, and then we'll close the terminal entirely. So we'll just save what we have done today. Today is lesson 21. So just want to make sure I actually have lesson 21 in there. And that's the name of the stream, isn't it? Just make sure. Yeah, 21. Okay, cool. So what we're going to do is we're going to end here, and I'm just going to make a note of what we've done today. So day 21, what did we do? We did implicit type conversion. We then did when it happens. And when it happens, standard conversions. we did floating point, and we did numerical promotion. We did floating point promotion. We did integral promotion. We did numeric promotion. We did safe versus unsafe conversion. And the 4 types. We did narrowing conversions. List and the loss of data. We did list, initialization, and const expression in initializers. Yeah. Yeah. We did arithmetic conversions. Yeah, and then we ended there with the ranking being so double is first, with the ranking being long double, double, float, long, and int, lowest, and long double is highest. Okay, cool. Tutto bene, and today's date is the 19th of August. Cool. So commit that. So that is going to be it for today. Hopefully you enjoyed and are enjoying C++ as much as I am. Get rid of that. And again, as always, if you saw something I did that I shouldn't have done, or you saw something that maybe I could have improved on, let me know. Yeah, and hopefully you're enjoying it like I am. And I'll see you in the next one, where we'll be doing explicit type conversion and static cast. So as always, please like, subscribe, and comment and all that good stuff. And I'll see you in the next one. Bye.